Despite the overwhelming darkness, despite the silence, despite the unimaginable distances, the universe feels close. The stars appear pinned to a dome above our heads. The Milky Way stretches gently across the sky like a cloud of glowing dust. It feels almost intimate, as if the cosmos were built on a human scale. But this feeling is an illusion. A deeply convincing illusion. Because the universe is not merely larger than we imagine, it is larger than our capacity to imagine. From the moment humans first lifted their eyes to the sky, we have tried to understand what we were seeing. Ancient civilizations mapped the heavens, believing the stars were fixed points embedded in a crystalline sphere. Later, we learned the Earth was not the center of everything. Then we learned the Sun was just one star among billions. And then came the most unsettling realization of all. Our galaxy itself is only one among hundreds of billions of galaxies. Each discovery did not simply expand the universe. It diminished us. And yet, paradoxically, it elevated us too. Because understanding the universe requires something extraordinary, a mind capable of grasping realities far removed from everyday experience. A mind capable of confronting scales so vast that intuition collapses. Consider this. Light, the fastest thing in the universe, travels nearly 300,000 kilometers every second. In the time it takes you to blink, light can circle the Earth more than 7 times. And yet, even at this speed, light takes over 8 minutes to reach us from the sun. That means when you feel sunlight on your skin, you are not experiencing the present. You are experiencing the sun as it was 8 minutes ago. Now extend that idea outward. Light from the nearest star beyond our sun, Proxima Centauri, takes over 4 years to reach Earth. Light from the center of our own galaxy takes 26,000 years. And light from distant galaxies may have been traveling toward us for billions of years. We are not looking across space. We are looking back in time. Every point of light in the night sky is a message from the past, delivered across incomprehensible distances. The universe does not reveal itself instantly. It whispers its history slowly, patiently, across the cosmic void. This alone should shatter our sense of scale. But it is only the beginning. The human scale problem. Human intuition evolved on Earth. Our brains are exquisitely tuned to survive in environments measured in meters, seconds, and kilograms. We understand distances we can walk. Timescales we can live through. Energies we can feel. The universe operates on none of these scales. A single galaxy contains hundreds of billions of stars. The observable universe spans 93 billion light-years. The mass-energy content of the cosmos is dominated by things we cannot see, dark matter and dark energy, whose nature remains mysterious. We are attempting to comprehend a reality that was not built for our understanding. And yet, somehow, we do. This is one of the quiet miracles of science. Mathematics allows us to stretch beyond intuition. Equations become ladders that let the mind climb beyond its biological limits. Through symbols and abstraction, we access realms that no human body could ever visit. But this intellectual access should not be mistaken for physical access. Understanding the universe does not mean we can traverse it. This distinction lies at the heart of a profound truth, one that science fiction often ignores, but physics insists upon. The universe is not merely difficult to cross. It may be fundamentally uncrossable. Distance as a physical barrier. In everyday life, distance is an inconvenience. A long commute. A delayed flight. A faraway city. In the universe, distance is something else entirely. It is a barrier enforced by the laws of physics. The Milky Way is approximately 100,000 light-years across. Even if we could travel at 10% the speed of light, far beyond any technology we can currently imagine, crossing our galaxy would take 1 million years. Not generations. Not civilizations. Geological epochs. During such a journey, continents would shift. Species would rise and fall. Entire languages would emerge and disappear. Earth itself might no longer resemble the planet we left behind. Interstellar travel is not just a technological problem. It is a civilizational problem. How do you build a society that can survive for hundreds of thousands of years inside a machine? How do you preserve culture, knowledge, and purpose across timescales that dwarf recorded history? And even if you solved all of that, distance presents another challenge. Energy. The energy wall. Motion is never free. To move faster, you must expend energy. To move much faster, you must expend enormous energy. And to approach the speed of light, energy requirements explode toward infinity. This is not a limitation of engineering. It is a law of nature. Einstein's theory of relativity reveals that as an object accelerates, its resistance to further acceleration increases. The closer you get to the speed of light, the more energy is required to gain even the tiniest additional speed. At the speed of light, this requirement becomes infinite. Infinite energy is not a future technology problem. It is an impossibility. This means that no object with mass, no spacecraft, no probe, no human. The cosmic speed limit is absolute. And once you accept this, a sobering realization follows: the universe is structured in such a way that most of it will always remain beyond our reach. The psychological consequence. This realization challenges a deeply held belief. For centuries, progress has meant overcoming limits. We crossed oceans. We climbed mountains. We split atoms. We walked on the moon. Each success reinforced the idea that limits are temporary. Physics tells a different story. Some limits are not technological. They are ontological, woven into the fabric of reality itself. The universe is not indifferent to our ambitions. It is indifferent to everything. And yet, this indifference does not render our efforts meaningless. In fact, it may do the opposite. If we cannot conquer the cosmos, perhaps we are meant to understand it instead. A shift in perspective. The dream of crossing galaxies is seductive. It speaks to adventure, expansion, and destiny. But physics gently redirects our attention. The real frontier is not distance. It is understanding. We may never visit distant galaxies, but through telescopes and equations, we reconstruct their birth, evolution, and fate. We understand nuclear reactions inside stars we will never see up close. We map cosmic structures spanning millions of light-years. The universe does not need us to travel through it. It allows us to comprehend it. And that may be the deeper gift. 1. Why space refuses to behave like distance on Earth. On Earth, distance is negotiable. If something is far away, we simply find a faster way to reach it. Horses gave way to trains. Trains gave way to planes. Each technological leap compressed the world, turning continents into neighborhoods. This history quietly programs our expectations. It convinces us that distance is a temporary inconvenience, something innovation will eventually erase. But space is not Earth scaled up. Space is governed by rules that have no counterpart in everyday life. In the cosmos, distance is not merely a matter of speed. It is inseparably bound to time, energy, and causality. To traverse space is to wrestle with the deepest structure of reality itself. And reality is not flexible. 2. The light year, a unit that hides a warning. Astronomers measure distance in light years, a unit that sounds poetic but carries an implicit warning. A light year is not a distance you can cover. It is a distance defined by time. 1 light year is how far light travels in 1 year, nearly 10 trillion kilometers. When we say a star is 1,000 light-years away, we are saying something more disturbing than, it is far. We are saying, even the fastest thing in the universe takes 1,000 years to get there. Distance in space is already time. And time, unlike distance on Earth, is not compressible beyond a point. 3. Why the speed of light is not about light. Despite its name, the speed of light is not fundamentally about light. It is the speed at which information, causality, and change propagate through spacetime. If something could travel faster than light, it would not merely arrive sooner, it would arrive before it left in some reference frames. Cause would follow effect. Events would lose their order. Reality would fracture. The universe avoids this paradox by enforcing an absolute limit. The speed of light is not a suggestion. It is a structural boundary. 4. Spacetime is not a passive stage. Newton imagined space and time as a silent stage where events unfold. Einstein showed that space and time are actors. Mass bends spacetime. Energy warps it. Motion reshapes it. When something moves through space, it is not gliding across an empty backdrop, it is interacting with spacetime itself. At high speeds, this interaction becomes violent. Time slows. Lengths contract. Energy skyrockets. The universe pushes back. 5. Why acceleration becomes increasingly futile. At low speeds, acceleration feels linear. Press harder, go faster. At relativistic speeds, acceleration becomes cruelly deceptive. Each increase in velocity demands more energy than the last. The relationship is exponential, not linear. You can pour unimaginable energy into a spacecraft and gain almost nothing in speed. It is like running toward a horizon that recedes faster than you can approach. The universe permits effort, but denies completion. 6. Time dilation, the misunderstood promise. Time dilation is often presented as a solution. If travelers move near the speed of light, their clocks slow down. From their perspective, long journeys become short. This is true, and deeply misleading. Time dilation does not shorten the universe. It shortens your connection to it. While the traveler experiences years, the universe experiences millennia. The destination changes. The origin disappears. Everything familiar dissolves. Time dilation does not allow you to cross space, it allows you to abandon time. 7. The communication breakdown. Even if a spacecraft could survive a relativistic journey, communication could not. Signals are limited by the same speed of light. A message sent halfway across the galaxy takes 50,000 years to arrive. No conversation. No feedback. No correction. A galactic traveler is not just distant, they are causally isolated. Once you leave, you are alone. 8. Space is not empty, and that matters. At everyday speeds, space feels empty. At relativistic speeds, it becomes deadly. A single hydrogen atom struck at near-light speed releases energy comparable to high-energy radiation. A grain of dust becomes catastrophic. Shielding against such impacts requires mass. Mass increases energy demand. Energy increases radiation exposure. The problem feeds on itself. Space turns hostile precisely when you try to move fastest. 9. Navigation in a moving universe. Space is not static. Stars orbit the galactic center. Galaxies drift. The universe expands. Over long journeys, destinations do not stay where they were. Navigation becomes probabilistic. Precision dissolves. At galactic scales, even aiming becomes uncertain. 10. The light cone, the universe's fence. Relativity introduces the concept of the light cone, the region of spacetime that can influence or be influenced by an event. Outside this cone, events are unreachable. Forever. Much of the universe already lies outside our light cone. Not far away, inaccessible. The universe is not fully connected. It is partitioned by causality. 11. Why faster is always worse. Going faster requires more energy. Increases danger. Magnifies isolation. Accelerates temporal separation. Speed does not conquer space. It intensifies its consequences. 12. The galaxy as a natural boundary. When all constraints are combined, light speed, energy, communication, radiation, and cosmic motion, the galaxy stops looking like a destination. It begins to resemble a boundary condition. Physics does not forbid motion across it. But it forbids meaningful interaction across it. 13. A sobering realization. We often imagine ourselves as future galactic explorers. Physics suggests something humbler. We are local creatures in a vast universe, permitted to observe far beyond where we can go. The universe allows knowledge to spread faster than bodies. That may not be a flaw. It may be intentional. 14. What this teaches us about meaning. If we cannot cross the galaxy, perhaps significance does not lie in expansion. Perhaps meaning is not measured in distance traveled, but in depth understood. The universe does not invite conquest. It invites comprehension. 15. Where the last hope appears. Still, one idea lingers. What if we do not move through space at all? What if we reshape spacetime itself, folding it, tunneling through it, bending it into shortcuts? Wormholes. Warp drives. These ideas sound like escape hatches. But physics is relentless. If distance is the first wall we encounter when imagining journeys across the galaxy, then time is the second, and far more deceptive, barrier. Because space does not exist alone. It is woven inseparably with time. To understand why crossing the galaxy may forever remain beyond our reach, we must confront one of the most revolutionary ideas ever discovered by science, Einstein's theory of relativity, and the profound limits it places on motion, energy, and causality itself. This is where intuition breaks down. Where common sense fails. And where the universe reveals rules that are as unforgiving as they are elegant. The end of absolute time. For most of human history, time was assumed to be universal. A single cosmic clock. Ticking identically for everyone, everywhere. Newton believed time flowed equably without relation to anything external. So did philosophers, astronomers, and engineers. But in the early 20th century, Albert Einstein shattered this assumption. Time, he discovered, is relative. It depends on motion. It depends on gravity. And it depends on how fast you move through space. Brian Greene often emphasizes that this is not a trick of perception, it is a physical reality, confirmed again and again by experiment. There is no master clock in the universe. Each observer carries their own time. Special relativity, motion changes time. Einstein's special theory of relativity rests on two simple principles. The laws of physics are the same for all observers moving at constant speeds. The speed of light in a vacuum is the same for everyone. No matter how fast they're moving. That second statement sounds harmless. It is not. It detonates classical physics. Because if light speed is fixed, then something else must give. And that something is time itself. Time dilation explained. Imagine a spacecraft traveling at 90% the speed of light. To the astronauts on board, everything feels normal. Their clocks tick normally. Their heartbeats are steady. But to an observer on Earth, those astronauts are aging more slowly. This is called time dilation. The faster you move through space, the slower you move through time. At 99.9% the speed of light, time nearly grinds to a crawl relative to Earth. Brian Greene often describes this as a cosmic trade-off. Motion through space eats away at motion through time. But here's the crucial point. You can never reach the speed of light. The infinite energy barrier. As an object accelerates, its energy increases. As it approaches the speed of light, that energy requirement diverges toward infinity. No matter how powerful your engine. No matter how advanced your technology. No matter how much fuel you carry. Reaching light speed requires infinite energy. And infinite energy does not exist in our universe. This is not a technological problem. It is a law of nature. Why this destroys interstellar dreams? Suppose we try to cross the Milky Way in a ship moving at 99.9999% the speed of light. From the crew's perspective, the journey might take only a few decades. But from Earth's perspective, tens of thousands of years would pass. Civilizations would rise and fall. Languages would die. Continents would shift. The travelers would return, if they returned at all, to a universe that no longer remembers them. Interstellar travel becomes not just a journey through space, but a one-way trip through time. The relativity of simultaneity. Relativity delivers another devastating blow to galactic travel. There is no universal now. Events that appear simultaneous to one observer are not simultaneous to another. If you and a distant civilization try to synchronize clocks, the concept itself becomes meaningless once high speeds are involved. This destroys the idea of real-time coordination across the galaxy. No galactic federation. No synchronized communication. No shared present. Just isolated bubbles of time, drifting apart. General relativity, gravity warps time itself. Einstein didn't stop with motion. In general relativity, gravity becomes geometry. Mass bends space. Space bends time. The stronger the gravity, the slower time flows. Near a black hole, time slows dramatically. At the event horizon, time nearly stops, relative to distant observers. This introduces new obstacles. Galactic travel would require navigating gravitational fields so extreme that clocks would desynchronize. Navigation would become chaotic. Structural forces could rip spacecraft apart. The universe is not a flat racetrack. It is a warped landscape. Energy limits of the cosmos. Every attempt to overcome distance runs into energy constraints. The total energy output of our sun is staggering. And yet, even if we captured all of it, it would be insufficient for sustained relativistic travel across the galaxy. To move significant mass near light speed requires energy on the scale of stars, not engines. Brian Greene often points out a sobering truth. The universe is generous with beauty, but stingy with energy. Cosmic rays, nature's failed experiments. The universe itself conducts experiments. Cosmic rays, subatomic particles accelerated by supernovae, approach light speed. They are nature's fastest travelers. And yet, they lose energy. They collide with background radiation. They decay over long distances. Even nature struggles to move information across cosmic scales. The speed of light as a causal firewall. The speed of light is not just about motion. It is about causality. Nothing can travel faster because information cannot propagate faster. If signals could exceed light speed, cause and effect would break. Effects could precede causes. Paradoxes would dominate reality. Physics would collapse. The universe enforces this limit ruthlessly.